All right. Yeah, so I'll show you an overview of the CGI flight masks. There's either an insane amount of information I could tell you, or just the overview, which is a lot less. So I opted for the lot less. Since we're a little behind schedule, maybe that means we'll make up a little time. But anyway, I guess, or if there are lots of questions, we can do that too. But all right.
I will let you know 3 minutes before the end of your talk, okay?
Sure. All right. All right, so this slide is really a description of the next slide, so I might as well just move on to that and I'll talk to you there. So just follow along with me here. There's a lot going on, but maybe you look at the left half of the slide, you can see that there are a dozen high contrast configurations in the instrument. But it's important to note that there are three main categories. There's the one required mask configuration. So that's the hybrid LEO chronograph doing narrow field of view imaging in band 1. And that was our primary one that we tested. But we also ended up having time to test the wide field of view shape pupil chronograph in band 1 as well. So even though that wasn't required, we ended up doing full system level testing of that in TVAC as well. There are 3 other like best effort chronographs, which are all shaped pupils that enable different capabilities, mostly spectroscopy and polarimetry, that we did not do full system level testing, but did do some basic imaging. So like we did not do wavefront control with these 3, but at least for the band 4 and band 3, we did some basic checkouts with the slit spectrograph and the Wollaston prism to check that we could take images as expected in the with polarimetry. And we did not actually take any images, I believe, in band 2 for that best effort one. And then there are a bunch of unsupported modes or mask configurations in the instrument as well. And for these, we really didn't do anything during integration and testing. These are all contributed by XEP and are kind of, what do you call it? It's masks that we had real estate to put them in the instrument, but there's no expectation that we will test them. But if everything goes well and there's time at the end of the mission on orbit, then people can potentially propose to use these. And on the right here, so this will all be kind of explained better in the paper, but there are the paper that I'm trying to write on this is meant to be more of a user guide to explain, if you're actually trying to use any of these, which of the masks in the instrument, do you use or do you combine along with the color filter to make this all work out? And what is the field of view, either in lambda over d or milliarc seconds on sky? It's I was trying to count how many masks there are in the instrument, and it's a little iffy what to count as a mask or not, like is an open position a mask, but I think it's something around 200, possibly more. So yeah, it's a little tricky to try to get too much detail about any one masking here. But all right, so in addition to the high contrast mask configurations that I ideally could get you all the way to 10⁻⁹ contrast, but who knows for some of them. In TVAC we got towards say 10⁻⁸. There are also ones that are just thrown in to kind of round out the capabilities, and these are essentially regular LEO chronographs where you either shouldn't or can't use wavefront control with them. In this case, because the occulting spots actually block all of the controllable region, but these are meant to just complement your low contrast or poor contrast capability if you want to see farther out, because the more you block, the larger the occulter, the more light suppression you get farther out. So, and then in addition to these unsupported Leo chronographs, you would just align and take images with. There's also a set of Zernike wavefront sensing dimples in the dielectric we have on some of the substrates. And that could let us try to do some real-time measurements of wavefront drifts. We sadly did not have time to test any of that, but again, that for Hab Worlds or something, someone may want to test that capability. And I'll just say again that these are all untested and kind of unsupported, but we thought we should at least have similar capabilities to Hubble with some of the Leo chronograph imaging. And if somebody doesn't want a giant occulter, you could also just use the small occulters from the hybrid Leo chronographs for poor contrast regular imaging. Right. And I guess I didn't mention what the rest of these capabilities are here, but for the other unsupported high contrast imaging modes, it was again to kind of round out the things that we thought would be useful if there's time after the main instruments mission. So doing spectroscopy in a different orientation was high up there. Doing, I guess that was already covered, the wide field in different bands. Having the narrow field of view with HLCs in the other 3 bands than the one required one. So bands 2, 3, and 4 was important. And the 2 mask configurations that are, kind of radically different and not, let's see, like I would say that by testing the 2 that we did, it gives us confidence that 8 of the other 10, so most of the shaped pupils and all the HLCs, that we would be able to just do the same thing, but in a different band, do the same wavefront correction procedures, and it would work. But for the multi-star wavefront control, there's different software that would have to be developed to implement that. So those 2 are a little bit different, but otherwise, again, like we could do the same procedures given extra time and money in the future to round out the instrument's capabilities. All right. So in this diagram, I didn't talk, didn't have a space here for, do you use this with the spectrograph or with the Wollaston prisms for polarimetry? And the answer is really that technically you can use you can do spectrometry and polarimetry in all 4 of the band passes. But the caveats are that, spectroscopy is nominally only intended for bands 2 and 3. And that's mostly just based on the 2 prisms being designed for bands 2 and 3 to be the most linear. So you would get more dispersion outside of those, but they're still usable. And then also just in terms of, intended usage, polarimetry was only kind of meant for bands 1 and 4, but you could also use it in between if you wanted. But because it's mostly shaped pupils with a limited field of view, it might be less useful trying to do that. So anyway, the points here are just that there are a lot of combinations and options, and I'm just trying to show you in these 3 slides what the main intent was, but somebody may be clever and come up with another combination that they would like to propose using in the future. And then just to make things extra complicated, there's kind of mix and match options with the field stops that you can use. So the field stops are not diffractive optics, right? So they literally just limit your field of view, which means that when you have 40 or so field stops, you could often use many of them with any of the mask configurations shown before. So again, there are ones that were intended for specific purposes, but you may be able to use different or use them interchangeably. So, things like the slits, many of those are interchangeable depending on what you want out of your slit. If you're doing spectroscopy, there are lots of circles, big ones trying to be more open but limit the field view a little bit for polarimetry. We have some emergency backup half dark hole options if we had to use that. And I guess really the main ones that we plan to use are, the circles for the small circles for the HLC to limit the field of view. Yeah, so anyway, these are, again, many options available, but I'll be listing out all the kind of intended purposes for that. And I'll finish out here with just some pretty pictures. So all of our flight masks were fabricated in JPL's Micro Devices laboratory. And they do a very good job, and everything came out to extremely high accuracy for how we specified them. So these are the flight masks for the HLC, at least the band 1, and some of these are used in other bands. But like here's the actual fused silica substrate, and you can see all the little tiny tiny dots. So this one here is the one we used in TVAC and FFT, and this is is this an AFM, I think, measurement of the surface height on that, which was made extremely accurately to get the diffraction that we wanted from it. And then these are through-hole masks for the LEO stop and field stop, were made also extremely accurately to within a few microns, or for the individual smaller masks, less than a micron edge error. So yeah.
3 minutes to wrap up.
Okay.
Thanks.
And yeah, on this slide, these are the shape pupil masks. Not all of them, because they're more for, say, the focal plane masks, but the shape pupils were all put on the same wafer. These also came out extremely accurately, something like 0.1 micron edge accuracy. Yeah, and the LEO stops and the field stops are the same for all the masks, so it's the same picture as the last slide. But yeah, so these are extremely high-performing devices that we have in there in lots of spaces. So I'll again have to go into more detail in the paper, but yeah, and I'll also explain in the paper, like what all the extra markings and stuff on here are. But so just to wrap up, what I've shown you is that we have just a bunch of possible options in the instrument to use, but for the required testing, there's just one, the narrow field of view in band 1, which we tested in TVAC, as well as a similar option for the wide field of view. So that's just 2 of the 12, and anything else is not part of the planned commissioning, and it's really up to the CPP after the main mission to use the rest of the kind of best effort and unsupported ones. And in addition to the intended modes, there are a ton of field stops can be used with each case, and so that will take some effort for the CPP to plan out what they should be using. And then finally, the as fabricated masks, we're able to successfully make all of them. So everything that we intended to put in the instrument ended up there. Okay, that is all. Thank you.
Thank you, AJ, for the grand tour of the different Coronagraph masks on the instrument. Before we go into questions, I want to remind folks that there's also a talk this afternoon that will tell us a little bit more about the manufacturing results of these masks. So maybe hold off if you have questions about manufacturing and tolerancing for Feng-Shi's talk this afternoon. Any questions for AJ? Yes, Nick.
Yeah, hi, AJ. Thanks for the summary. The unsupported mask that interests me the most is
the Zernike wavefront sensor dimples because Haberls probably or will likely need it. Have we ever passed any light through it? Are we semi-confident that it can be aligned? And I know we need flight software as well, but I'm just more interested in the alignment.
Maybe just adding to Nick's question, so Nick, can you also introduce how this mask is different from the regular loaves that we are using, which is also based on the Zernike reference sensor? So before answering that question from Nick, just tell us a little bit what that particular mask is doing that the other loaves is not doing.
Yeah, so so the low order wavefront sensor is a Zernike wavefront sensor, so a phase contrast wavefront sensor, except that's reflection only. And so we tried to pull a magic trick and have a mask configuration where you get both transmissive and reflective. So on both detectors, you have two different, like using the same set of masks, the same effect going on. So you wanted to have, a pi/2 phase shift, both in reflection and transmission. We designed it to do that, but did not have the details for the AR coding, unfortunately, that it's on. So it may not behave exactly the way we want in transmission. It's a little bit, unfortunately, aligning onto it is a little bit tricky. There are alignment spots to the left and right. So if you can align to those alignment spots and then do a dead reckoning move to the middle, then you can, I think, adjust to be centered correctly on the wavefront sensor. But it's kind of complicated, and we did not, unfortunately, have the time to kind of flesh that out. But I think it's possible. We may have spend time on that in the future.
Thank you.
Given
We have
funding.
up to
Okay.
one question, unfortunately, here. In the interest of time, and go to the next presentation.